going to be a walkthrough on how to complete example 2C2 in the dynamics textbook. So we start with a diagram that looks much like this, and then we're also given the length of each member in terms of L, as well as the angular velocity at member OA, as well as we can deduct the angular acceleration at member OA as well. And through that, we need to find the angular velocity at members AB and member BB. We also need to find the angular acceleration at members AB and BB. So to start with, we need to find the instant centers at each member. And for members OA and BD, it's pretty simple because they're both pinned connections. And those pins are where the instant centers are for each member. For member AB, it is also relatively simple. You can deduct from it, since the velocity at each member is parallel to it, that instant center is going to be to infinity. And from that, we can deduct that the angular velocity at member AB is 0. So the next step is we're going to use the instant center equation for member OA. And basically what we get is that we can find the angular velocity is equal to, or the magnitude of the angular velocity is equal to the magnitude of velocity at A over the magnitude of position vector for the instant center 2 point A. And with that, we can find that the velocity at A is equal to the angular velocity of member OA times the length of that member. And then in the next step, we're going to use the angular velocity of AB, which we found, and plug that into the velocity equation between members B and A. And we do that because it will send this term right here to 0, because it's a cross product with the position vector of BA. And through that, we can also find that the velocity at B is equal to the velocity at A. And also, we can find that the velocity at B is equal to the negative angular velocity of member OA times L. And then next up, what we're going to do is we're going to use the instant center equation again for member BD in order to find the angular velocity of BD. And same process as member OA, we're going to do the same thing with that, and we can deduct from that that the angular velocity at BD is equal to the angular velocity at OA over 2. With that, we're going to plug that into the acceleration equations given in chapter 2. And from this, it's mainly plug and chug given those. And since we know that the angular acceleration at member OA is 0, that sends this term to 0, and then we also know that the acceleration at the origin is 0 because it's a fixed point, so that sends that term to 0 as well. And that will give us that the acceleration for member A, or at A, is equal to the negative angular velocity of member OA squared times the length of that member. And that's going to be in the J direction. And then we can also do, in the next step, we're going to plug in the acceleration equation for member BA. So we're going to get that the acceleration at B is equal to the acceleration at A. And we go through here, this is multiplication, but since we found earlier that the angular velocity is 0 for member AB, this whole term goes to 0. And one thing that you can specifically note here is that this cross product is going to be slightly more difficult than the other ones because the other cross products were just in the I direction or in the X direction. And this one, we specifically have 2 components since this member is angled. So 2L is going to be in the I direction, and then L is going to be in the J. And that's going to give you that, well, basically through that, we find one equation for the acceleration of B, and we star that for use later. And then in part 7, we're going to do the same thing, but we're going to find the angular acceleration for B in terms, or from member D. So the first one we went from member B from A, now we're going member B from D. And you go through the same steps as previous, and this will give you another equation for the acceleration of B. And what you can do is you can set these equal to each other because both of these equations have terms that are equal to the angular acceleration for them. So the acceleration at B has a term for the angular acceleration for member AB. And then the acceleration at B in terms of D gives you in terms of the acceleration, or angular acceleration at member BD. So what you can do is you can set those equal to each other, and then through that, through some simple algebra, you can deduct that you can deduct and find the angular acceleration at AB and the angular acceleration at